Great.
Okay, well, let's see. Okay, well, thank you very much for the introduction, Colin, and thanks to you and your co-organizers for putting on such a wonderful conference. Putting on something of this magnitude must have been quite a challenge, and you guys have done a great job. So it's also a particular pleasure, actually, for me to be involved in this celebration of Lou's birthday. I've known Lou for over 50 years. And in fact, he and I were actually born on exactly the same date in exactly the same year. However, we're not the same age. So I know some of you already know this, but if you don't already know this, that's a little puzzle for you to work out when you get bored with the talk. So there we are. Anyway, so I'm going to talk about surfaces in the force sphere, knots of surfaces in the force sphere. So let's see here. Now, how can I wait? Oh, I see. Let's see. What do I do? I'm trying to. Can you see the whole page there? Or
I think we can.
okay, I can't. Let's see. How do I get it? Okay, well done. Okay. Anyway, yeah. So I'm gonna let's see. So F is. I'm gonna look at closed, connected, orientable surfaces of some genus, locally flat, PL embedded in the force sphere, and that's equivalent to looking at smooth surfaces. But because I'm going to be talking about decision problems, it's convenient to think of PL surfaces, but at least then it's clear that you know the objects of our study can be described by a finite amount of data. Okay, and such a surface is said to be unknotted if it's an ambient isotopy, taking it to a Heegard surface in the equatorial 3 sphere. Equivalently, if it bounds a handle body. Now, as we know in dimension 4, there are sort of a priori two different concepts here. We could ask for the isotopy to be PL or just purely topological. And so we have two notions of the surfaces being PL unknotted and topologically unknotted. So the question I'm interested in is the unknotting problem for surfaces in S4 solvable? In other words, is there an algorithm to decide whether or not a given surface in S4 is PL or top unknotted? Let me put this in some context by pointing out that an interesting special case of this, of course, is when the genus of the surface is 0. So F is just a 2-sphere, and then we call F a 2-knot. And more generally, of course, one can look at an n-knot, which would be a locally flat PLN sphere embedded in the n+2 sphere. And it turns out that the unknotting problem for n-knots, you can ask about that, and it's known that that's solvable when n is 1. That's, of course, a classical theorem of Haken. Interestingly, my understanding is I think this was a bit of a surprise because this was proved in the late 1950s. And in the 1950s, these various sort of decision problems were being imported into topology. And the theorems were all of the form, you know, this and that is unsolvable. In fact, even Alan Turing, in a popular article he wrote in 1954, suggested that the unknotting problem for knots, for classical knots, might in fact be unsolvable. So Haken, the result was a little bit of a surprise. Anyway, but it is solvable in that dimension. For n greater than equal to 3, it's unsolvable. This was proved by Nabotovsky and Weinberger. A different proof was given by Gonzalez Acuna, Jonathan Simon, and myself. So it's unsolvable there. And I might mention that in those dimensions that I just mentioned, the PL and topological unknotted concepts are in fact equivalent. So there's no need to distinguish it. For n equals 1, this is a classical theorem of Moïse. And for n greater than equal to 3, again, it follows from a theorem of Levine. Okay, so we're solvable for n equals 1, unsolvable for n greater than 3. Of course, we're unknown for n equals 2. So I'd love to be able to settle this, but I'm not going to be able to do that. But instead of looking at two spheres, as I said, I'll look at surfaces of higher genus. And at this point, let me say that the fundamental group of the complement of the surface, I'll denote that by pi of f, and that's just the group of f. And that's going to play a sort of key role in what I have to say, as I'll explain. In particular, a theorem, a relatively recent theorem that's going to play a key role in what I'm going to say is a theorem of Conway and Powell that says that a surface in S4 of genus at least 3 is topologically unknotted if and only if its group is Z. So obviously, an unknotted surface has group Z, and for genus greater than 3 in the topological category, this is equivalent by the Conway-Powell theorem. So like I said, I'd love to be able to answer the question for the two spheres, but unfortunately I can't. But let's see. Let me just state a couple of theorems right off the bat here that the topological unknotting problem for surfaces of genus at least 24 is unsolvable. So that's a theorem that I'll spend most of the time talking about, actually. In the PL category, you can't do quite as well. At least I can't. The PL unknotting problem there is you need genus at least 25. Okay. So let me make a remark. Obviously, there are other questions you might ask in this vein. There are analogs of these theorems for non-orientable surfaces. You might ask, what about non-orientable surfaces in S4? People study those. And you could also look at two spheres in other four manifolds. Like I said, I mean, perhaps one's basically interested in the case of two spheres in S4. Well, I've kind of weakened that to say, well, let's talk about surfaces of arbitrary genus in S4. You could also look at two spheres in other four manifolds, for example, connected sums of S2 cross S2. So in fact, there are theorems along these lines, but I'll state them, but I won't say anything about the proofs. So for the non-orientable surfaces, for embeddings of connected sums of RP2 and S4, the topological unknotting problem is unsolvable as soon as you have at least 73 projective planes. And in the PL case, as long as you have at least 77. These numbers seem a little high, but anyway, okay, it's all a matter of perspective. And then for the other problem, for two spheres, for embeddings of S2, and for example, the connected sums of S2 cross S2, you get completely analogous theorems as to theorems 1 and 2. Namely, the topological unknotting problem is unsolvable as long as you have at least 24 copies of S2 cross S2 and 25 in the PL category. So let me say something before I get into the details of the proof of theorem 1 and theorem 2. Let me say something about, as I said, the group will play a key role in this. And the point about this is ultimately, all these unsolvability problems reduce to the fact that there are finitely presented groups with unsolvable word problem. And I mean, this goes back to in the 1930s, people were looking at various notions of computability and proving various unsolvability problems. For example, Turing proved the unsolvability of the halting problem for Turing machines. And then by the 1940s, this was being imported into mathematics. And famously, it was shown that there are finitely presented semigroups with unsolvable word problem. And then finally, in the 1950s, it was shown that there are actually finitely presented groups with unsolvable word problem. So that'll be a key ingredient to what I have to say. So let me say a little bit about that. So this is the famous Novikov-Boone theorem that there exists finitely presented groups, G. So there you have a certain number of generators and a finite number of relators with unsolvable word problem. That means that there's no algorithm to decide whether or not a given word in the generators represents the identity element of the group. And I'll have occasion to refer to this later, so I'll use that notation. W equals it was G above the equal sign, meaning that this word W represents the identity in the group. Okay, so this was then used to show the unsolvability of many problems in group theory. For example, well, by many people, but Adyan and Rabin sort of systematized that initially. So let me just explain how that goes. It's not that mysterious. You just have to do it, of course. But once you have a finally presented group with unsolvable word problems, suppose you want to prove that you can't decide whether a given finally presented group is trivial or not. That's a triviality problem. Well, what you need to do, if you can come up with a construction that starts with a finitely presented group with unsolvable word problem and a word in the generators, if you can then take that data and show how to algorithmically construct a finite presentation of a group, let's call it G sub W, it'll depend on W. And then if you can prove that if the word W represents the identity in G, then G sub W is the trivial group. And if the word does not represent the identity, then G sub W is not the trivial group. Well, then you've reduced the triviality problem to the word problem. And so the triviality problem would be unsolvable. And usually what happens in practice is to prove that if the word is not, if the word does not represent identity, the fact that your group G sub W is not trivial, if you could prove that the original group G embeds in G sub W, then of course you'd have done that. And so that usually these proofs end up proving embedding theorems as well. At least the techniques can be used to prove various embedding theorems, which I'll mention a couple of those. And then, okay, so we're now firmly in mathematics and group theory. And of course, similarly, the existence of finitely presented groups with unsolvable word problem can be used to prove the unsolvability of certain problems in topology. So famously, the homeomorphism problem for closed four manifolds, Markov, the fact that you can't recognize the n sphere for n greater than or equal to 5. In other words, if you're given an n manifold, n greater than or equal to 5, can you decide whether or not it's homeomorphic to the n sphere? Well, the answer is you can't. This is a different Novikov, by the way. This Novikov is the son of this Novikov. This is PS Novikov. This is SP Novikov. And again, of course, the one I just mentioned, the unknotting problem for n knots. So again, the basic inputs of all these theorems are the existence of groups with unsolvable word problem. Let me say a little bit. I mean, this is one of my little hobby horses here about the homeomorphism problem for closed four manifolds. You see, like I said, there are groups with unsolvable word problem, and you can't. You can use that to show that you can't decide whether or not two groups are isomorphic, and so on and so on. And so finitely presented groups. On the other hand, you know that for any finitely presented group, there is a four manifold, a closed four manifold with that fundamental group. And so it seems pretty clear that you should be able to prove that the homeomorphism problem is unsolvable. However, I would point out that it's not immediate. You have to do some work, because certainly every finitely presented group is the fundamental group of a closed four manifold. But every finitely presented group is also the fundamental group of a finite simplicial 2 complex. And the homeomorphism problem for a finite simplicial 2 complex is actually solvable. So that's always something to bear in mind when one thinks about these problems. Okay, so going back to n knots, one thing that Gonzalez Acuna and Simon and I proved was that in higher dimensions, for n greater than 3, there's an n knot group that has unsolvable word problem. By the way, the reason that for n knot groups n greater than 3, there's a beautiful sort of purely algebraic characterization of these groups due to Curvaire. And the fact that the analogous problems are unknown in dimension for 2 knots is the fact that there's no such characterization of 2 knot groups. So I think that's a very important kind of question. But I should mention that we proved this theorem actually. Sorry, this theorem actually implies the unsolvability of the Unknotting problem for n knots, n equal to 3. It's not obvious that it implies that, but it does. And again, getting back to 2 knots, we conjectured in that paper that there's a 2-knot group with unsolvable word problem. And if that were true, then that would imply the unsolvability of the unknotting problems for 2 knots. I would like to say, it's an old joke, but I like to say that we're 99% sure that this conjecture is true. You know, each of us is 33% sure. So I don't know. I'd love to be able to solve it, but I'm not going to do that. Anyway, I'm not going to be able to show that there is a 2-knot unsolvable word problem. But again, if we allow surfaces of higher genus, in fact, there is a surface of genus 24 whose group is unsolvable word problem. By the way, that's the same. I mean, 24 is the same everywhere. So that's the same 24 that appeared in Theorem 1. But this Theorem 5 does not obviously imply Theorem 1. So, and finally, let me just mention this in passing as a kind of joke. I mean, there's an amusing consequence of some of the stuff we do here is that there's actually a surface at S4 of genus 174 whose group contains an isomorphic copy of every finitely presented group. So that's an interesting surface, right? Of course, the heavy lifting is done is Higmann's theorem, but let me skip over that. Okay, so let me start going towards the proof of the theorems 1 and 2. So let me briefly mention Wirtinger presentations. So a Wirtinger presentation is a finite group presentation with generators x1 to xm related to r1 to rn, and each relation is this very special form. It says that each relator says that some generator xi is conjugate to some generator xj, possibly the same generator. So W is just some arbitrary word in the generators. And I think in this context, these presentations were first introduced by Yajima. And so here's an elementary, well-known lemma that we'll use. If you have a Wirtinger presentation like that, if the first homology is Z, then W is the group of a surface in S4 of genus n minus n plus 1. So the genus is the number of relators minus the number of generators plus 1. And this is very easy. Many of you know this. So you start with an unlink of M2 spheres in S4. So these correspond to your generators, X1 through XM. These are the meridians of the 2 spheres. And now you just tube these spheres together by tubes according to the relators. In other words, if you tube the ith sphere, if you want to realize a relator like this, you tube the ith sphere to the jth sphere. You give orientations to the sphere so that these meridians have signs, and you do it in such a way that the orientation is preserved. And then this word W, this is just some word, that's going to be the word in the x's that's sort of that's represented by the core of the tube as you link around the spheres and so on. Okay, so you do this and you get an orientable surface that has its group is the group you started with. And then finally you say, well, what's the genus? Well, first of all, the assumption that the first homology is Z, that means that all the generators have been sort of connected up, right? Which means that you've connected up all the spheres, so you do get a connected surface. And then finally, an easy computation says that the order characteristic of the surface, on the one hand, it's 2 minus twice the genus. On the other hand, it's twice the number of spheres minus twice the number of tubes. And so you get that the genus is what we claimed it was, n minus n plus 1. Okay, so that's how I'm going to construct surfaces in S4. So many people will recognize that these are in fact ribbon surfaces, and that does play a role in some of the other theorems, but it's not important for us at the moment. So let me. I'm going to focus on just really giving a proof of the first theorem, which says that the unknotting problem is unsolvable in the topological category for surface of genus 24 or more. So as I said, the key input is going to be the existence of finely presented groups with unsolvable word problems. And if I just wanted to show that there was some surface of some genus, that there was some genus such that the topological unknotting problem for a surface of that genus was unsolvable, I could just use any finite presented group with unsolvable word problem. But I want to get the genus as low as possible, right? And so, but for that reason, I'm going to introduce this sort of technical condition. It's just an ad hoc sort of technical condition that that works. Okay, so I'm going to say that a finite presentation of a group G has property star if it satisfies the following two conditions. So we've got M generators. So the first two commute, x1 and x2 commute. And then the second condition is just about what happens when you abelianize the group. Namely, if you abelianize the group and kill all the generators except x1 and x2, so you kill these, and you set x1 equal to x2, then you get z, generated by the image of x1. So that's just a very technical condition, but it'll enable us to play some little tricks. And notice this implies, of course, this implies that x1 and x2 certainly have infinite order, right? Because you know each one maps to something of infinite order when you abelianize and kill these guys. Okay, so now the proposition that is going to enable us to prove the theorem is this. So this is the main proposition, and I'm going to really give a proof of this. So this says that there's an algorithm that takes a presentation with this property star, and a word in the generators, and produces a Wirtinger presentation with two generators and two n+1 relations. I'm going to call that group W sub little w because it depends on the word. And this Wirtinger presentation, the group has, first of all, is z, and here's the key property, that it'll be isomorphic to z if and only if the word W represented the identity element in the group G presented here with property star, okay? So that's the main theory. And let me just notice that, of course, so this is a Wirtinger presentation of a group. So this group is a group of some surface, which I'll call F sub W. And what's the genus of that surface? Well, this presentation, the Wirtinger presentation, has two n+1 relations and two generators. And so the lemma that I just proved said that this WW, it's a group of a surface in S4 of genus 2n, if I've done the arithmetic correctly. All right, 2n. So now we go from a group, you know, a 100% group in a word to a surface of this genus. And then remember, n is the number of relators, remember, in the original group G that we started with. And now we can now just apply a Conway-Powell to say that, well, okay, construct that surface so that there's an algorithm that takes a presentation of group G with property star and a word W in the generators and produces a surface, F sub W in S4 of genus 2n. And remember, the point about this group was that it's Z if and only if W was the identity in G. Well, by Conway and Powell, that says that FW is topologically unknotted if and only if the word is trivial. So this is it. So now, once we have the proposition, we now have this by Conway and Powell. And now we just need to take G to be a group with unsolvable word problem. And we want n to be as small as possible. And we want it to have property star just so that the argument I'm going to give sort of works. And of course, this property star was chosen from, I mean, so the record actually if you want to finally present a group with unsolvable word problem, the number of generators isn't important, but the number of relators, the smallest number that's been realized is due to Borisov. So he showed it as a group with unsolvable word problem with 12 relators, 12 related presentation. And it turns out to have this property star, which was why I used it. So we can use it, okay. And so now we're done. That proves theorem 1, right? At least it proves theorem 1 for genus 24, right? because if you could decide whether or not this guy was totally unknotted, you'd be able to decide whether or not this word was the trivial element in this group G, but you can't. That's Borisov's theorem. And for genus greater than 24, you just take connected song with unknotted tori. That doesn't change the groups involved, you see. And so if you've got it for genus 24, you've got it for all higher genera as well. Okay. So let me prove the proposition. So remember, let me go back and remind you what the proposition is. I've got a presentation of a group G that has these two funny properties, and I want to come up and I take a word in the generators, and I want to come up with a two-generator presentation. It's a Wirtinger presentation with two n+1 relators with these properties. Okay, so here's a proof of the proposition. Okay, so I'm going to start off with my finite presentation of this group G with property star, and I'm going to take a word in the generators. And okay, and I'm going to, it's not sort of that important, but the commutator, I guess I'll use this notation for the commutator x inverse y inverse x y. Okay, so I'm going to define, I alluded to this kind of philosophy a few slides ago, the Adjan Rabin work. And I want to define a presentation of a group G sub W. It's going to depend on W. And it's going to be defined as follows. I take the same generators of x1 through xm of G, and I throw in four more, A, alpha, B, and beta. So those are the generators. And then what are the relators? Well, I'm still going to keep the relations in G, R1 through Rn, but then I'm going to throw in some more. So here's the ones I'm going to throw in. So if you think about it, there are going to be m plus 3. M is the number of generators of the original group G. So if you look at this, there are going to be, so there's 1, 2, these are two fairly innocent looking relations just involving A alpha and B and A alpha B beta. This one involves the word W. These ones, there are M of them, and they involve the generators X sub I of the original group. And the word W sort of comes in here. And I want to focus on those two in a little while. But let me just note for the moment, obviously I'm going to come back and explain why this makes some sense. Let's just notice for the moment, though, I'm sure you've already noticed that the elements on the left, these words on the left, they represent elements in the free product of the group G with the free group on A and alpha. So the stuff on the left just involves Xi's and A and alpha. So it represents elements in this free product. Similarly, the elements on the right, they represent elements in the free group on B and beta. Okay. So I'm going to make some claims about this presentation, G sub W. So this defines a group, G sub W, right? Okay. And the first thing I want to claim is that that the first homology of this is Z. If I Abelianize G sub W, I get Z. So let's just do that because, okay, so if you Abelianize it, well, first of all, you Abelianize G. So you get H1 of G. And then let's go back and look at the relations. When you Abelianize everything, the first relation just says alpha is equal to B squared. The second one just says A is equal to beta. This one says that A is equal to B. Now, this one says that Xi is equal to B for I equals 1 and 2. And then this one says that Xi alpha is B squared for the remaining ones. But alpha is equal to B squared. And so that means that Xi is equal to 1. And so I've just written down what I just said there. Okay. So for I greater than equal to 3, Abelianizing gives us relation. But you see that that implies Xi is equal to 1 because alpha is equal to B squared. This is when we Abelianize. Okay. And notice that by property star, you see, by the second part, you know, remember when I said if you Abelianize G and you kill all the relations except the first two and you set the first two equal, then you get Z. Well, there you go, generated by that. So clearly this now is just Z, generated by A or generated by B or whatever, you know. Okay. Okay, so that proves that if we Abelianize this group G sub W, by the way, this group G sub W, that's not going to be our Wirtinger group. There's going to be one step beyond this, but this is going to be the kind of first approximation to it. Okay, so abelianizing the group gives us Z. The next thing to notice is that G sub W is actually generated by A and B. So let me go back and explain that. And in fact, not only will we see that it's generated by A and B, but we'll see how to get a presentation on those generators. You see, I can use the first relation to express alpha as a word in A and B. So I can just, in all the subsequent relations, if alpha appears, I just replace it by that word in A and B and delete this relation. Similarly, this second relation, I can express beta as a word in A and B because I've already expressed alpha as a word in A and B. And so then I can replace beta by that word in A and B and remove this relation. Let's move on to these last three. See, this says that xi, it's a word in B, beta, A, and alpha. Well, but I've expressed all those in terms of A and B. And so we can express xi as a word in A and B and delete the corresponding relation. So we get rid of all these. The only slightly tricky one, perhaps, is this one, because this involves W. And W is a word in all the x's. But you see, I've got this relation here. And this commutator, actually, this is A, W inverse A inverse W. Well, W inverse AW is a word in B and beta. So that can be expressed as a word in A and B. So I can express this guy as a word in A and B, and then I can replace xi, I equals 1 and 2 by that word. And so I've got rid of everything except A and B. And in fact, this procedure proves not only is it generated by A and B, but in fact, we've got a relation, we've got a presentation like this where you have the two generators A and B. The only relation that's left, apart from apart from the original ones involving the x's, is just the one that said W inverse AW is equal to beta inverse B beta. And so you're just left with one relation that says A is a conjugate of B. And then you've got all these relators here. These are just the RIs, the RJs, rewritten as words in A and B, see, because each xi is now a word in A and B. So we've now got that group G sub W. Okay, it's got a very nice, it's just a two generator. This is going to be important. It's two generators, and it's got this one relation here, and then these others that came from the original G. Okay, but again, okay, this group G sub W depends on W. So I want to claim, so what happens if the word happened to be the trivial element of G, in the original group? Well, that relator that said W inverse AW is beta inverse B beta, that would imply that A is B inverse B beta, right? And then if you look at the relations involving x1 and x2, if I kill W, if W is trivial, then those commutators, I mean, I can go back and have a look. You see, these commutators become trivial. And so if W is 1, this just says that x1 is beta to the minus 2 B beta squared. And x2 is beta to the minus 3 B beta cubed. So those relations become very simple. Right, they become that. But remember, x1 and x2 are supposed to commute in G. This is one of those technical conditions. And so that means that these two guys commute. So that means that B and B inverse B beta commute just by conjugating. But B inverse B beta is A if W is 1. And so A and B commute. But the group's generated by A and B. And so it must be abelian, and therefore it must be Z because it abelianizes to Z. So this is good. If the word W represents the trivial element of the original group, then this GW is Z. Now, what happens if the word is not the identity? Well, then I claim, and this is a reason for writing down these sort of slightly bizarre-looking relations, maybe. I claim that the elements on the left-hand side, I'll go back there, they're actually a basis for a free subgroup of this free product, G star, the free group, and A and alpha. And similarly, the elements involving B and beta, they form a basis for a free subgroup of the free group in B and beta. And this is actually very easy. I mean, let's go back. Let's take the right-hand side, because that's a little, I mean, it's just, you just got B's and betas. So what you need to show is that these guys are a basis for a free subgroup. of the free group on B and beta. And that's really easy. So you think of these guys, let's call them Y sub I or something. There are M plus 3 of them. And if you just take some reduced word in the Y's, in other words, you're allowed positive or negative powers of the Y's, but you don't want any Y inverse to be next to any, Y and so on. And then you just look at what kind of cancellation can you, if you now write them out in terms of B's and beta, what kind of cancellation could you have between adjacent Y's? Well, you can't really have any. I mean, that's, if you just think about it. See, these powers are all different. I mean, and so on. And so you're not going to, and similarly, a B can never cancel with a beta. A B squared could cancel with a B inverse, but you're still going to be left with a B. Anyway, so there you go. So this is, and similarly here, I mean, it's just an easy check. One thing I should say, you need this xi to have infinite order, because if this had finite order, then this, of course, would have finite order, and you would not get a free subgroup. But again, remember, that was one of the consequences of this technical condition star is that x1 and x2 actually have infinite order. And so it works, okay. And so the upshot is that if the word is not trivial, then this G sub W, it's a huge group. It's a free product with amalgamation. It's the thing on the left, the thing on the right, amalgamate along a free subgroup of rank M plus 3. That's the number of relations there, you see. And so it's certainly not isomorphic to Z, right? So, okay, that's G sub W. But now G sub W, that's not a Wirtinger presentation. So now we just have to move to a Wirtinger presentation. And that's very easy. We just take the same presentation, but except instead of killing the S sub J's, we just make them central. So we just say that they commute with A and B. And now we've got two generators and two N plus 1 relations. And that was what I was claiming. And again, you can easily see that the first homology is Z. And what happens if I set all the SJs equal to 1? Well, I get an epimorphism from phi from this group onto the G sub W. And the kernel is obviously central, right? Because the kernel is the normal closure of the S's. And so if the word W is not equal to 1, well, I just pointed out that G sub W is not Z. And so certainly WW is not Z, okay? Because it maps onto G sub W. On the other hand, if the word is 1 in G, then G sub W is Z. And that implies that the kernel of phi is just the commutator subgroup of W sub W. But because the first homology of W sub W is Z, that means that the lower central series stabilizes immediately at the second term. So the commutator subgroup is actually the next term in the lower central series. But that's clearly 1 because the kernel of phi, which is this is central. And so we conclude, in fact, that the kernel of phi is trivial. And so W sub W is also isomorphic to Z. So that proves our proposition. We've come up with this Wirtinger presentation with two generators, two N plus 1 relators. So it gives you a surface of genus 2N. And it's going to be Z if this word is trivial in the group, and it's going to be not Z if the word is not true. And so if we choose our group G to be Borisov's group and so on, then we're done. Okay, so that proves theorem 1. Let me just briefly say something about theorem 2. This is the PL case. So there, we're just going to take a connected sum of the guys I've been talking about with an unknotted torus. Let me call that F prime sub W. That doesn't change the group. And so if our word W is not the identity in this group G, then the corresponding surface FW prime is certainly going to be knotted because its group is not Z, so it's only going to be PL knotted. On the other hand, let's remember that, now what happens if the word is 1? Well, remember that F sub W, we got it from this Wirtinger presentation with two generators. So that means we took two spheres and we tubed them together. So we just had two spheres, S1 and S2, and a bunch of tubes. Now, if we let FW star be FW, we add a tube connecting S1 and S2 so as to give an unknotted two-sphere S0. So obviously we can add a tube to do that. And let's call the result FW star. Well, you see, if we think of, another way to think of FW star is that we can first add the tube connecting S1 and S2 to get S0. Well, that's an unknotted sphere, so its group is Z. So when we add more tubes to get FW star, you see, because homotopy is the same as isotopy in this dimension, this is just Z, and so these tubes are all going to be trivial. And so this surface is going to be PL unknotted. And this was an observation of Miyazaki. This shows that more generally, the unknotting number of a ribbon surface, is at most the number of spheres that you start with. And so then we say, well, but on the other hand, if this is true, by the way, see, this argument is true no matter what the word is. But finally, if the word is trivial in G, then pi, the group of FW is Z, right? And so when we add this tube H, that's the same as just adding a trivial tube, see? And so FW star is going to be PL isotopic to F prime W, and this guy's unknotted. So the upshot is, I hope that's a little fast, but the upshot is that if the word is 1, then this guy is actually going to be PL unknotted. So at the expense of adding one more tube, one more copy of the torus, then we get corresponding theorem to PL category. And the fact that we only needed one tube was because this group W said we only had 2 generators. Okay. So that proves theorem 2. So let me just finish with, obviously one would like to improve the bounds in these theorems. It reminds me, whenever you go for a physical and the doctor says, oh, I've had a look at your cholesterol. I'd like to get these numbers down a bit, Well, I'd like to get these numbers down a bit, especially the numbers for the non-orientable surfaces. And also this 174. By the way, the numbers have already come down considerably since I first started thinking about these things. So, you get hooked. But anyway, let me just finish by basically repeating some things I said right at the beginning. Obviously, what you'd really like to know is the is the unknown problem for 2 knots solvable. And similarly, of course, you could ask for the simplest non-orientable case, RP2s. Is that solvable? And again, finally, let me come back to this conjecture that we made with Fico and Jonathan. Is there a 2-knot group with unsolvable Bohr problem? I think it's a great question. We conjectured the answer is yes, but I mean, whatever. It's interesting either way. And as I said, the problem is that it's not really clear, what class of groups, 2-knot groups are. And again, finally, one reason this would be interesting is that if there is such a thing, then you know that the unknotting problem for 2 knots would be unsolvable. So it remains only for me to wish Lou a happy birthday and to answer the puzzle. You see, yeah, we were both born on 2, 3, 4, 5, which I think you'll agree is a great date to be born if you're a low-dimensional topologist, actually. But the thing is that Lou was born in the US and I was born in Scotland. So although it's the same date, it's actually different days. So there we are. Anyway, thank you very much for your attention and happy birthday, Lou.